continue our investigations on the effect of negative feedback on amplifier. We will show shortly that incorporation of negative feedback in amplifiers can bring the features which we really require in an amplifier. Besides the stability, we can modify several other parameters also. Now, we continue and take that how this negative feedback in an amplifier can result in a much reduced nonlinear distortion. So, reduction in nonlinear distortion. Reduction in nonlinear distortion. I talked briefly in the previous lecture about the nonlinearity, the characteristics, the input characteristics, output characteristics of a transistor, whether it is BJT or it is FET, they are in certain regions they are nonlinear, and there are various other components. We can't assume the complete linearity about their behavior. Now, we saw earlier that how stability is achieved by incorporating negative feedback. Now, we study that this distortion, because distortion will finally come in the form of voltage fluctuation. So, for example, if a circuit shows without incorporating feedback a distortion of the order of 10%, that means if the output voltage is 10, then because of these fluctuations it may be plus minus 10, that means it may vary from 11 to 9 volts. Now, this fluctuation can be controlled, can be minimized by incorporating the negative feedback. It may be reduced to just 1% or 2%. You have to decide how much you want, because this will again, as you will see, will depend on the fundamental expression AFB, that is gain with feedback is equal to A, that is gain without feedback, divided by 1 plus BA, where B is the feedback factor and so on. Now, the distortion, nonlinear distortion may be defined as D. This is for open loop. Definition is same for open loop or closed loop. So, let us take for open loop, this is change in gain divided by gain, that is dA by A, and if this change is small, it is infinitesimally small, then this delta can be taken as differential. So, the distortion in open loop amplifier can be represented by dA by A. In the same way, for the feedback amplifier, the distortion can be written as DFB, distortion with feedback, this is equal to A DAFB by AFB. Now, we have to arrive at a relation between D and DFB. In between these two distortions, we have to find what is the relation. We make use of the fundamental equation of the gains, how the gains are related in a non feedback and with feedback amplifier. This is A f b equal to A 1 plus B A. We use this equation and we differentiate it with respect to A. So, differentiating with respect to gain A, then we get one plus B A d A minus B A d A by 1 plus B A square, which this, if we open it, then this term cancels and we are left with d A f b. This is equal to d A into 1 plus V A square. Now, this can be rewritten by breaking this square term by writing two terms, so that it becomes d A f b is d A by 1 plus V A into 1 by 1 plus B A. And for this 1 plus, we can write from the fundamental relation this one. We can write that 1 by 1 plus B A, we can write as A f b by A. So, this term we replace by d f. From here this is A f b by A. Therefore, this equation becomes d A f b is equal to d A 1 plus B A into A f b by A. I have replaced that 1 by 1 plus B A from the fundamental equation in this ratio, because we want to bring the expression, final expression, in a format which we can immediately use and which is having the same terms which we are aware of. So, this can be now rewritten in the form d A f b by, we take this on this side, A f b equal to d A by this A into 1 by 1 plus B A. And you remember how we defined, these are the defining equations. Here this is the distortion, nonlinear distortion in a with negative feedback, and this term is the distortion, nonlinear distortion for a amplifier without feedback. So, this is equal to d f b, nonlinear distortion with feedback, this is equal to, and this is d by 1 plus B A. This is the expression which shows that the distortion, nonlinear distortion in a amplifier with negative feedback can be reduced over the nonlinear distortion of open loop amplifier by a factor 1 plus B A. We have seen in the one example which was taken that if this term is 10, for example, there it was 100, that means that distortion will be 100 times reduced, and if it is less, if it is 50, it will be reduced by 50 times. If we set this as 10, then it will reduce to 1/10, the distortion will remain only 1/10. So, we can decide how much modification we want. Remember, by bringing this term more and more, the sacrifice of the gain will be of the same magnitude. If this parameter is 100, then distortion is reduced to 1/100th, but gain will also be reduced to that extent. It will be 1/100th of what it was in the absence of the gain of the feedback, negative feedback. Now, in the negative feedback itself, there are different configurations possible, and they give rise to different types of negative feedback. So, different types of negative feedback. There are, depending on how we connect the feedback network at the input and output, that will decide that what type of configuration we are going to have, and how we will, what factor will decide, that will be you will see that it will influence properties of interest, whether we make a shunt connection at output or a series connection at output, similarly at the input. So, there are 4 possible negative circuits, negative feedback amplifiers, 4 different types of configurations. Four different types. First is voltage series feedback, voltage series feedback, and this is also called actually or series shunt feedback. In this nomenclature, this talks about the input connection, that how feedback network is connected to the basic amplifier at input, and this is at output. While in this configuration, this stands what we are feeding back, the output fraction of the output voltage or current. So, it is voltage or current feedback, but how we return that signal, how we mix that signal at the input in series or shunt. So, this terminology, this is for the input side, this is for the output side, while in this nomenclature, this is the input side, this is the output side. Now, so for voltage series feedback, this connection is this. this is the load resistance R L, and this is the basic amplifier, and having gain A. This is the feedback network, with gain B, and then V E. This is the current, and this is the output current. So, this is the configuration, and here you remember that we are sampling the output voltage. So, plus minus V 0 is the input to the feedback network, and what appears here is V f with this polarity, and this is V e error signal, which is coming from the mixture of these two signals V s and V f. The feedback signal V f in this circuit will vary according to how the variations occur in V 0. The output impedance of the amplifier will decide what is the fraction of that we are feeding back to the input. This is one configuration. Here see carefully and remember that at the output there is a shunt connection. We are taking it in parallel and we are returning it in series. So, this is sampling the voltage, and the gain here of course will be the voltage gain. Then this is one circuit. So, at the input this has series connection. At the output it has shunt connection. And we sample the voltage, fraction of the voltage is fed back, and that becomes the part of the input. This is one kind, that is voltage series feedback or series shunt feedback. The second type is, once we take this we will see that how we take actual circuits, actual amplifier circuits for these. At the moment we are showing them in block diagrams. So, this is current series feedback. Current series feedback, or this is series. And the circuit for this is This is the basic amplifier with gain A. This is the feedback network, and here the gain is B. Now, and this is the error signal V E, and this is V F with polarity plus minus. So, this is the current series feedback. Why we call current series? Because the voltage which we are feeding back the voltage, and this voltage will vary according to the in proportion to the output current I 0. This current will decide when it flows through this feedback network, then it will generate a voltage which becomes the part of the input and hence the negative feedback. This is current series feedback, and V E, one thing to remember is V E is the return signal which varies in proportion to the output current I 0. This is the second type. Then the third type this is current shunt feedback type. Third is current shunt feedback. Or shunt series feedback. The circuit is this. This is basic amplifier, gain A, and this is feedback network, gain B. This is load resistance, and here we will connect the signal which will generate the input current I I. Now, I 0, this sends current I F I F. Here we are feeding back the current I F, which is the outcome which goes from the feedback network. So, and I F varies in proportion, I F varies in proportion to I 0, and here. So, we are sampling, actually we are feeding a fraction of the output current, and it is mixed with it is compared with the input current I and which goes in this circuit, and the circuit functions. In this nomenclature, shunt connection at the input, series connection at the output, and in this nomenclature we are sampling the current and returning that signal into shunt form at the input. So, this is current shunt feedback or shunt series feedback. And the fourth and the last is fourth and the last is voltage shunt feedback. Which is also known as shunt feedback. And the circuit for this is basic amplifier having gain A, open loop gain, and this is feedback network having gain B. And in this we are sampling the output voltage, fraction of the output voltage we are sampling, and the current which will be dependent, which will vary in proportion to the output voltage V 0. This is the current which will be compared at the input with the input current I I, and so I f is proportional to V 0 and this I f is compared here. So, this is voltage shunt feedback. I just summarize these 4 circuits, the 4 types of, because they are very important, they will modify the impedance levels at the input output differently. And here this is the voltage series feedback, or this is series at the input or shunt at the output. Voltage series feedback, current series feedback, current shunt feedback, and the fourth one is voltage shunt feedback. So, 2 possibilities with current shunt, current series, and 2 possibilities with voltage shunt and voltage series. Now, we take that how we will choose that which of these 4 configurations we are going to select, how we select. We will select, we will make only one out of it in a circuit. We can't incorporate 2 or 3 different types of feedbacks in one circuit, that will not work. We have to choose out of these 4 configurations one configuration, and what will be the deciding factor, because they are going to affect the impedance levels. So, that impedance levels whether we want to increase or decrease. So, that will decide that which of these configurations we are going to incorporate. So, now we study further, these were all the basics. Now, we really see that how the effect of negative impedance, what is the effect of negative feedback on impedance levels. Effect of negative feedback on input and output impedances. effect of negative feedback on input and output impedances of an amplifier. I have been saying this, and I am sure now you have understood this statement, that all properties in a negative feedback amplifier are modified to the tune of 1 plus B A, that we will see here also. Now, we are studying the impact of negative feedback on input and output impedances. Now, see, and I am saying that the changes will be of the order of this. Whether it increases, it will increase by this amount. If it falls, it will fall by this amount, meaning that the input impedance, if the input impedance for open loop amplifier the input impedance of the open loop amplifier, suppose this is Z I. Z I is the input impedance when we do not attach the negative feedback, we do not incorporate the negative feedback, and with negative feedback, with negative feedback, this may be, if it is, this has to increase, then Z I with feedback will become 1 plus B A of Z I. Similarly, if the output impedance without feedback, now let me complete here itself, and if it has to fall, then Z I input impedance with feedback will be reduced to this. Two things, one thing is, this is a positive parameter, positive quantity, a positive number, and this can be 10, 20, 100, depends on your design, and your design is what you, how much, for example, increase in the input impedance you require. Similarly, here it will decrease in the similar fashion. Now, as a guiding principle, you remember, if we have two resistances of 2 k each, for example, very elementary example I am taking so that you grasp the concept. If they are connected in series, 2 k resistance, effective resistance is 4 k, that increases. So, remember, if we are talking of input impedance, if connection is series connection at the input, then input impedance will increase. If the same impedances 2 k and 2 k impedances, if they are connected in parallel, this is 2 k, this is 2 k, they are connected in parallel, then apply the simple that resistance rule, then you know it will come out to be k, 1 by 2 k plus 1 by 2 k is equal to 1 by effective resistance, and that comes out to be k. So, this is reduced to k. So, in shunt they reduce, in series they are they increase. So, when at the input, if the connection is series connection, you remember shunt and series we have been talking in these 4 configurations. So, if the input is a series resistance, the resistance will increase by the factor 1 plus B A. If it is shunt resistance, this will decrease, and this will be by the factor 1 plus B A again. Similarly, at the output, if the connection is shunt, then output impedance will fall. If it is in series, the output impedance will rise. So, remember this basic fundamental. We derive an expression for the input and output impedance. I take just one example each at the input and output, and similarly the analysis can be done for all the 4 circuits, because we have to devote time for other things. So, all the 4 analyses are not required to be taken, but as an example only one I take, that is voltage series negative feedback. Voltage series negative feedback amplifier. For this amplifier, we will determine the after incorporating the negative feedback, what will be the input impedance and what will be the input impedance, what will be the output impedance. The circuit is this. Basic amplifier, gain A, this is the feedback network, and here the gain is B and R L this is the applied input signal V s. This is alternating, but we show at an instant when this is positive, and similarly here this is V 0 and here is plus minus V e. This is the circuit which from where we started, the first circuit, same circuit, voltage series feedback circuit. Here at the input is the series connection and at the output is the shunt connection. So, this is voltage series feedback. We measure the impedance here. If we measure between these 2 terminals, that will be the input impedance without feedback, and when we measure between these 2 terminals from here to here, this will be Z I F B with feedback, because this does not, we exclude this. So, when we measure the input impedance here, this will be open loop input impedance, but when we incorporate it, that is between this terminal and this terminal, when we measure the input impedance, it will be Z I F B. So, by definition in this circuit, Z I, which is input impedance for open loop, input impedance for open loop amplifier. This is obviously, if the current here we take as I, the voltage is V e. So, this is V e, simple Ohm's law, by I. This is Z I is the impedance without feedback, open loop impedance. So, remember this definition, and then in the same way look at this circuit. Here the input was V e, here the input is V s. So, for feedback circuit, Z I feedback, this is equal to V s by I. Now, And what is our purpose? Our objective here is to show that what is the relationship in this circuit voltage series negative feedback, what is the relationship between Z I F B and Z I. What is the relationship? This is what we are driving by simple analysis. This is simple, but it is complete analysis. There is nothing like detailed analysis for these amplifiers. And so, now you remember that the error signal that comes because of the superposition of the return signal, and here in this amplifier the return signal is V f, and I am sure you have not forgotten the basic equations. The input V 0, the output V f. So, obviously, B is equal to V 0 by V f. This is superimposed over the input signal V s. So, the error signal is V s minus V f, and from what I have written, B is V f by V 0. Therefore, V f is equal to B into V 0. This we substitute here, then V e becomes V s minus B V 0. From here, what is the value of V s? V s is simply V e plus B V 0. And now, you know that A was the open loop gain, and open loop gain in this circuit you can see, if the input is V e, output is V 0, then the gain is V 0 by V e. So, A is V 0 by V e, or simply V 0 is A into V e, A into V e, that we substitute here. So, that this expression becomes V e plus B A into V e, this is V s, or V s equal to V e 1 plus V a. From here we can immediately obtain, if we divide both sides, dividing both sides by I, the input current, we get V s I equal to V e I into 1 plus B a. And what is this? This is, look here how we defined, this is the input impedance with feedback, and this is the open loop impedance, impedance of the open loop. Therefore, we get the relationship from here that Z I F B is equal to Z I into 1 plus B A. This is the relation. We get the relation that how much modification in the input impedance will occur in this voltage series circuit which is under consideration by incorporating feedback. The input impedance becomes high by the factor 1 plus B A, and this is again because this is a series connection at the input, and I threw those 2K resistances example, the resistance was supposed to increase. So, it has increased. If Z I is 1 kilo ohm, 1 kilo ohm, and if this factor is for example 10 or 100, say 100, let B A, because one can always be neglected in comparison to A B normally, and let it be 100, then the impedance with feedback, negative feedback, will become 100 kilo ohms. Very interesting. Negative feedback in the circuit enhances the input impedance if the connection is voltage series negative feedback. In fact, for all wherever the input is in series, the resistance will be this much. I will summarize little later, but this is the thing. When the connection at the input is in series, feedback connection is in series, the impedance relationship will be this. And then let us find out the output impedance. The output impedance. Output impedance for the amplifier under investigation, and which amplifier we are investigating? Voltage series negative feedback. And for this, now we have to apply, we have to find out the expression. The objective is to find out the expression output impedance with feedback, how it is related with ZO, that means the output impedance without feedback. Suppose you are given any circuit and we ask you that find out the impedance, what you will do? You will apply a test signal, a small voltage, and find out the resulting current, and the ratio of the two will give you the impedance. Similarly, so the rules of the game here are that we have to find out the impedance here, the output impedance here, and this can be done. The first thing which we will have to do is we have to remove this load resistance. Load resistance is not included. This is the general principles of the analysis, that when output impedance is to be taken, take out that resistance and connect a voltage source Vx. So, when we do that, and we will observe the corresponding current Ix. So, the what we are talking is this. This is basic amplifier, gain A, this is feedback network, gain B. Here we have removed that resistance RL, maintaining the same connection. This is a test voltage Vx, which sends a current Ix. And remember, besides when we are talking of output voltage, then the input signal Vs is to be set to 0, and a test signal is connected at the output. And here this is V e, This is the return signal V f. The output impedance with feedback is equal to the ratio of the test signal and resulting current I x. This is the test signal, this is the current which is generated, and the amount of current will depend obviously on the impedance, output impedance of the circuit. Now, from the above figure and from we already understand that V e, the error signal, which is the sum of V s minus V f, but in the present case V s is 0, we have reduced the V s to 0. So, since V s is 0, V e is equal to minus V f, and V f here, this voltage is plus minus V x. So, obviously, V is output is V f, input is V x. So, V f is equal to B into V x. This is the input to the feedback circuit, this is the output. So, output to input, this is the ratio which gives V f equal to V x, and that V f we substitute here. So, then since V f is equal to B into V x, our error voltage becomes minus B V x. We draw a equivalent circuit for the output port. In this, we just take the output port and we draw the circuit. So, from the equivalent circuit, for the output port, I draw it here, and then we arrived at a small simple relation. This is the impedance Z0, and here we have connected V x, which has sent current I x, and here is another voltage source from where it will arise here. This signal is amplified A times. So, what is the voltage here? V e into A times it is amplified. So, this is A V e. I hope there are no confusions about it. One voltage we have connected, the other voltage will appear because of V e, which is amplified A times. So, that there are two voltage sources. Now, it is simple that we can find out the value of I x. If we have a resistance and one terminal is at potential V x, at the other terminal is connected is having a potential A V e, then obviously the current will be the difference of these two potentials, that is V x, simple Ohm's law, minus A V e divided by Z 0. This is the relation which we get, and now we substitute for V e what we have found out here. Here we substitute this V e by minus B x. So, what we get? The relationship for I x becomes equal to V x plus B A into V x by Z 0, because V e, the error signal as we have shown above, is minus B V x, and from here we come out to be, this is I x is equal to V x, we take common 1 plus B A by Z 0, or output impedance with feedback by definition is V x by I x, and this is equal to Z 0 1 plus, that is Z 0 F B Z 0 1 plus V A. This is the relation, that how the output impedance will be reduced by the factor 1 plus V A. As I said in the beginning, the same thing we are now finding, that in this configuration the output is having a shunt expression, shunt connection, and shunt connection is going to reduce the amplitude of the magnitude of the impedance, and this is reduced, all variations are governed by the factor 1 plus B A, and therefore, this is the impedance. And in fact, so this relationship, this I have derived just for one output and one output, but the analysis can continue for all. Just to summarize, in the table, that the feedback configuration, this is the input impedance and impedance, and this is the output impedance. Here without feedback, this is Z I, and output impedance is Z 0. In voltage series feedback, this increases to Z I F B is equal to Z I 1 plus B A, and this is reduced because this is actually series shunt. So, at the output is shunt. So, Z 0 F B is equal to Z 0 1 plus B A. For current series feedback, this both increase, Z I F B becomes Z I 1 plus B A, and similarly output becomes Z O F B equal to Z O into 1 plus B A. For voltage shunt feedback, this is reduced F B Z I 1 plus B A, this is increased, this is also reduced, Z 0 is, so all kinds of combinations are there, and finally and lastly this is I can just say that this is current shunt, this is reduced Z I F B, it is reduced Z I 1 plus B A, and this is increased Z 0 F B, this is Z 0 into 1 plus B A. This is how the impedance levels are changed, are modified by the incorporation of the negative feedback.